lecturer, Martin Sommerfeld, that is a big friend of us, and we like him a lot. And in this second talk Professor Sommerfeld is given to us in this spring school is called Particle Interactions in Dispersed Multiphase Flows. So let's take a look in this. I believe we can start, Professor, and the guys is coming. Okay, thank you, Professor.
Thank you very much for the introduction. Thank you for the invitation, and I'm happy to be here again in Blumenau. And after my first lecture, which was more related to particle transport, I will now focus on the interaction of particles in dispersed multi-phase flow. You see here in our picture from a landing airplane, due to condensation, droplets are formed, and the droplets are somehow clustering in the flow structure, and you clearly can see the vortices developing at the winglet, for example, and further downstream of the wing. So this is one issue I will address during my presentation. So after an introduction of the interaction phenomena, I will talk about the importance of interparticle collisions. Then I will look at the fluid dynamic interaction of two particles only, not like tons, many particles, and see how the drag force is affected. And this is again done some years ago by Lattice-Boltzmann method. Then I will move to the Euler-Lagrangian point particle tracking and collision modeling. And here I will emphasize the difference between discrete particle method and discrete element method. There is a really distinct difference. And Jonathan asked me to talk about agglomeration, and I will introduce in which way you can model agglomeration. There are different levels, you can do that, and actually we had also a comparison of the different models and compared the outcome. The major part is devoted to our structure agglomeration model, using homogeneous isotropic turbulence, which is quite complex, but it gives good answers. And finally, I move to the results of Oskar Sprott, who is coming here from Blumenau, and he developed the open form code with regards to particle collisions and agglomeration, and he applied it to a cycle. So particle interaction, of course, become important if there are many particles, so if the volume fraction becomes high and the interparticle spacing is getting smaller. And of course, another important issue is the relative velocity. If there is no relative velocity, they will not collide. So change in relative velocity is mostly also associated with the change in time. So we can distinguish between three interaction phenomena. That is first the partial fluid dynamic interaction between particles due to the modification of the flow field around the particle, which is also important for small Reynolds numbers, but more important for large Reynolds numbers. This fluid dynamic interaction I will introduce with an example. And such a fluid dynamic interaction, I mentioned that already, is also called three-way coupling, according to Clayton FURB. And in practice, this is done, Hans mentioned that briefly, by introducing the swarm drag. And nowadays, of course, we have the options to do DNS to evaluate this swarm drag. Then we have the short-range interaction when the particles are coming close together. This is an illustration of the long-range fluid dynamic interaction and short-range interaction. When the particles are close before contact, you have a kind of lubrication. The liquid has to be squeezed out, and you know, okay, air has no inertia, but water, for example, has an inertia. Lubrication is much stronger. And then you also have other forces like electrostatic forces and van der Waals forces. And eventually you have a collision, which can result in a rebound or in a sticking of the two particles and forming a agglomerate. What do interparticle collisions do in a particle-laden flow? And I mainly concentrate on particles. The issue, of course, becomes more complicated if you have droplets or bubbles. So you have a momentum transfer between particles. That means also you have a redispersion when there is a high concentration region of particles. You have many collisions between the particles. They redisperse into the flow by interparticle collisions. However, they can be also trapped by interparticle collisions. Then you might have agglomeration due to the adhesion of fine solid particles. In process engineering, these collisions are also used to grind the particles by interparticle collisions. The particles are breaking and destroyed. And yeah, at the end, I mentioned the problem of coalescence and droplet collisions or bubbles. So this is again a similar picture I showed Monday. We can first of all distinguish between dilute two-phase flow, dense two-phase flow. Dilute two-phase flow is mainly governed by fluid dynamic transport of the particles. We have to account for all the relevant forces, of course. And when we go into the dense situation, of course, we have fluid dynamic interaction and collisions between the particles. Another issue which is resulting from the particle interaction is the clustering and segregation that mainly comes from the fluid dynamic interaction between the particles. So you can see, for example, particle clustering in vortical structures, which of course reduce the mixture quality. In many processes, you want to produce a nice mixture, for example, in a stirred vessel. Then you have, as illustrated here from the group of Professor Pritching, droplet clustering in sprays, which of course may reduce heat and mass transfer in this situation. And finally, an example is particle segregation in pneumatic conveying, which is often used for pulverized coal-fired plants. So this also destroys the mixture quality and reduces the combustion. And this is one picture illustrating the effect in pneumatic conveying. I said interparticle collisions redisperse dense regions, but here they are trapped. You see, this is two-way coupled. I mentioned it. So it's two- and three-way and four-way coupled. You see a large rope developing along the bend. But now, in four-way coupling, you see a much more narrow rope. That means particles being rebound from the wall are hit by other particles and pushed back to the wall. So you not only have inertia driving the particles towards the outer wall, but you also have particle collision. So I showed this picture already on Monday, just to repeat it. You can use the interparticle spacing and the volume fraction, of course, to distinguish between the different approaches, one-way coupled, two-way coupled, and four-way coupled, which is occurring in the dense region. So here the interparticle spacing is less than 10. This is, of course, a static picture. You still need a relative velocity to get collisions, but this gives you an idea when you have to account for interparticle collisions or interactions between the particles. A nice picture was also drawn by Otto. He distinguished these three regions. On the left-hand side, we have the very dilute system, fluid dynamic transport of the particles. So when L over D is larger than 10, then in the immediate region, here are the volume fractions up to 10%, and the interparticle spacing is between 2 and 10. Then you have the collision-driven regime, so you have a very frequent interparticle collision. And then on the right-hand side, you have the contact-dominated regime, where the interparticle spacing is less than 2, volume fraction more than 10%, and Hans mentioned that already in a fluidized bed of in a fixed bed is clear. So, of course, in this regime, we will see that we have to apply also different numerical methods because we have multiple contacts. So coming to interparticle collisions, first of all, we can have a look on the collision frequency obtained from the kinetic theory of gases. It's the collision cross-section times the relative velocity times the local particle concentration. So the collision cross-section is given by the size of the particles, of the two particles colliding. The relative velocity is induced by the surrounding flow. Then the particles are affected by flow transport and the number concentration. And collision between the particles can be induced by various physical phenomena. The relative velocity is 1, so if you have different sized particles, they are sedimenting with different velocities, so they will collide. That's the last one, mean drift between particles of different size. Then there is Brownian or thermal motion, which means particles, when they are small enough, they have random motion, called Brownian motion, resulting from the interaction of the particles with the molecules. So they have not straight trajectories, they have fluctuating trajectories and collide. It's the same in a turbulent flow. So different particles experience different history of the flow, so they have different velocity and they might collide, as illustrated here. So that's also when the particles are partially responsive to the flow. So then we have laminar or turbulent shear. So in a shear flow, particles, of course, have different velocities due to the response to the shear flow. So these are the basic mechanisms of interparticle collision, which can be described also by theoretical models. There are numerous models in literature, for example, Brownian motion by the Shulakowski equation. And we use now two other approaches or models showing the limit, low Stokes number limit and large Stokes number limit. Remember, the Stokes number is the response time of the particle over a characteristic time scale of the flow. This picture, or distinguishing between dilute and dense, was also introduced by Clayton Crowe. And it is based on a comparison of the time scale. Very important. Stokes number is an important number. And we compare here the particle response time over the collision time scale. So collision time scale is the time, the average time between subsequent collisions between two particles. Okay, so if this tau c is much larger than tau p, particle changes velocity in the flow, and then at some stage collides with another particle and changes again velocity. So this regime, the particle motion, is driven by the fluid dynamic interaction, more dilute. And on the right-hand side, we have tau p now being much larger than the collision time scale. So before the particle can respond to the flow, to the vortical structures of turbulence, it experiences a collision and changes velocity. So tau c is smaller than tau p. This is the dense flow regime, driven not only by collisions, but affected strongly by collisions between particles. So coming to some of these theoretical correlations, when you look at particles moving in a turbulent flow through turbulent eddies, then on Monday, they are very inertial particles, care about turbulence, and they are fully responsive particles. And in the intermediate regime, particles are partially responding to turbulence. And when they take different paths through the turbulent structure, of course, they will have different velocities. So the more the particles respond to the flow, the smaller the Stokes number is. This reduces the interparticle collision. frequency. So again, the degree of correlation can be decided by the Stokes number, particle response time or relaxation time, over a certain time scale of turbulence, which can be an integral time scale, or a Kolmogorov time scale, which is often used in DNF. As I said, there are various correlations describing the collision rate, number of collisions per volume. For Stokes number towards 0, Sussman and Turner derived this correlation, so depending on the dissipation rate here and the collision cross-section. And the other correlation for completely uncorrelated particles, very inertial particles, we don't care about turbulence, is coming, for example, from Abraham, with some limitations or assumptions in the model, no external forces, monodispersed particles. So looking at this result shows you also, gives you also an idea about our modeling efforts we had to do. So you have here 3 curves. The lower curve, independence of Stokes number, collision frequency, independence of Stokes number. The Sussman and Turner gives a constant value over all Stokes numbers. Then the Abramson, which is the kinetic theory limit, so particles do not respond to the flow, gives you a decrease of the collision rate with increasing Stokes. But the reality is in between, as I told you. Small particles cannot collide so frequently, as shown by this correlation. They follow the flow, they follow each other and do not collide. So the reality is somewhere here, and this is again LBM simulation my student has done many years ago. In this case, not a DNS, not a resolved simulation, but a point particle. That is Boltzmann combined with a point particle approach. So and the result is this one, which is in between, accounting for the correlation between partially responsive particles. So that you would expect the collision rate in a turbulent situation when you vary the Stokes number or the particle size, or he has done actually varied the density of the particles. So then this was basically the introduction to interparticle collision, hydrodynamic interaction. Now I would like to show some basics on the fluid dynamic interaction between particles. What happens to the drag force, for example? And Mr. Hölzer, who actually, and this is not very often respected, was the first one doing a parametric study on the forces acting on non-spherical particles with fully resolved DNS. So what we did here is, again, a computational box. The box is not seen on all sides. We placed 2 particles in there, spherical particles. One is the central sphere, and the other one is the analyzer sphere, which is moved around this central sphere at various distances, and we evaluate the drag coefficient acting on forces, all forces, also lift coefficient, on this analyzed sphere. Typical conditions are inflow uniform velocity, at the side place 0 gradient, and outflow also 0 gradient. Here are some dimensions, D 12 cells only. And I explained that on Monday, that is Boltzmann has this big advantage. We don't need so many or such a big resolution like 20 or 30 cells, because we have a different boundary condition. Or we evaluate the forces acting on the particles in a different way. They come out from the bounce-back boundary condition. But if you, of course, want to resolve temperature distribution inside the droplet, as Hans has done, this is probably not sufficient. So then this is the entrance distance to the front sphere is 8 diameters, then the outlet of the rear sphere is 15 diameters, and from the side face is only 3 diameters. might be not sufficient, but we would just wanted to get an idea about the interaction. So you see here some simulation, and I mentioned that already on Monday. You see that the flow field is somehow wiggling. This comes from the boundary condition, of course, although we use this interpolated second order boundary condition to capture correctly the contour of the particle. So, but actually, to get this flow field and the boundary layer also correctly, would need the better voltage. So you see here at low Reynolds number, the single sphere, a large stagnation point region, and of course a smaller wake region compared to higher Reynolds numbers. Then you have here the tandem arrangement and side-by-side arrangement. And we can, of course, evaluate the forces on the analyzer sphere from this bounce-back procedure. So at low Reynolds number, first of all, we have a large stagnation region. Then in the tandem arrangement, we have very low velocities, of course, in this region, and you also influence the pressure difference. So you should notice that blue is a low pressure and red is a high pressure. I didn't find the color scheme. And you can expect from that that the back sphere will experience a much lower drag. Then side by side arrangement, normally you have a drag increase. You have relatively high velocities, but not, you know, the truck effect. If you overtake a truck with your car, you are sucked towards the truck. This is not so pronounced at low Reynolds number, more at high Reynolds number, as shown here. So you have, first of all, smaller stagnation regions. You have a larger weight, and you have a wide, low pressure region around the equator of the sphere. On this side, which of course gives you a strong interaction and this sucking effect when the spheres are close together. You overtake the truck. So that's just a picture at low Reynolds number and the 45 degree arrangement, and here at higher Reynolds number. So we varied the angle of the analyzer sphere positioned around the central sphere, and these results are all shown for a distance of 1.5 diameters. And at the moment, we looked only on identical sized particles. So this is the outcome at the end. That's the contours of the drag coefficient for the second sphere with respect to the fourth sphere. And you see that the values given here are the drag coefficient of the single sphere and the average drag coefficient of the analyzer sphere, looking at all positions and all distances. So you see that the average drag is only slightly higher for the single sphere. So actually you have a slight drag reduction for the second analyzer sphere. This is Reynolds number 1, 50, 100, and 200. So when you go toward, I made here this line which shows the mean value of single sphere drag, and you see that the side-by-side arrangement gives a drag increase, whereas when the second sphere is placed behind the first sphere, you have a drag reduction. And this, of course, is changing from low Reynolds number to high Reynolds number. So we know that the flow field being disturbed by the sphere, it's much bigger in a low Reynolds number situation than in a high Reynolds number situation. So also this region in the wake is more of the drag reduction is more narrow. So as a summary from that, we have here the drag coefficient of the analyzer sphere versus the Reynolds number. We have the points are data from literature, experimental data points. We also take a Schiller or Namon correlation for that. And then first of all, the stars are the single sphere simulation. which are excellently matching the expected value, the Schiller-Naumann correlation. So for evaluating the forces on these particles, it's sufficient to take only 12 cells in the spherical particle. It's sufficient. But if you want to analyze more, like boundary layers and flow field in more detail, then you need, of course, the better resolution. Then we have also evaluated the maximum drag from this arrangement. So it's from all positions, we take the maximum value, which is here, it's slightly above the here. And the minimum value of the drag coefficient here is, of course, below the standard drag. On the right-hand side, you have the mean drag over the single particle drag, and you see clearly that short distances, this is the distance between the two particles, you have a strong drag reduction in average. If you move farther away, of course, this drag reduction is reduced, except for the small Reynolds number, at Reynolds number 1, the drag becomes larger than the single sphere pressure. So it's a way of analyzing the effect of one particle on the other. I mentioned already probably on Monday, I don't like when I do correlations or reflection and study unless they are derived from DNS, because you impose an Eulerian measurement, which is a measurement over this, on a Lagrangian effect. So what you should do, and I think people are doing that now, when you have a particle in a cluster, they use a random process to evaluate the change of the drag. Of course, we have two spheres. There you have a kind of drag reduction, but if you have many spheres, we have the single settling. A cluster of particles is settling much lower than a single particle. So this, I think this kind of work is already in development. Hence, I'm not so much in dense systems, fluidized bed, that people do a kind of random process to have a kind of Lagrangian modification of the drag coefficient, or increase of the drag coefficient. Okay, so let's move back to the Lagrangian point particle simulations. And as I said, I would put emphasis on the distinction between the different methods being used. So we have the Eulerian method, of course, to calculate flow field, and then the particles affect the flow field.
Forces, and here you have to select properly the forces acting on the particle. You cannot say ad hoc only the drag. I always ask when people present something about fluidized beds, they just use the drag. What about lift? It's not so important, but there is an effect, and I think some people already showed that there is an effect. So I distinguish between these three concepts. I think the oldest one is the Lagrangian parcel concept, because this Lagrangian approach was developed from spray simulations at Los Alamos. And in order to fulfill the mass balance, you track computational which represent a certain number of real. You cannot billions. So you say you take parts. In this part, droplets with the same size, with the same
way. And also, the collision is done in the same way. And Guericke introduced, for example, this semi-deterministic or stochastic collision model. Mostly here in this kind of simulations, you use a hard-scale collision model. And even people use it for bubbles. or droplet, which can be only a fluid. Then we have the discrete particle method. So you track all the particles. The particles are moved based on the fluid forces, the interfacial forces, and external forces, of course. And when you want to account for collision, you do that as a hard sphere collision, but this has a certain requirement. Hard sphere means the particles collide and bounce back, so the collision time is very short. Therefore, you have to restrict your time step. So if your time step is too large, you have multiple collisions, then you make an error. You can only capture one collision within one time step, so you have to reduce the time step accordingly. People use in this kind of simulations deterministic or stochastic collision models. Deterministic means I search for a possible collision partner among the tracked particles. Stochastic means, I will tell you more about that, you create a collision partner. Then we have DPM. I'm not a fan of DPM, but it's a very, very nice method because you can go to very dense systems. You can resolve multiple particle contacts, and each contact is treated as a soft sphere contact. So in some sense, you also resolve the penetration. The time step has to be very small or is driven by this penetration. Of course, you could do simulations with all real particles. There are some models, like this partial model, treating a particle as a cluster, but then you need to tune the constants to get the same answer. I hope I told you correct. You are specialists in DEM. So, you track all real particles. When you track the particle, you also include in the equation of motion the interaction force, the adhesion force. I will show more about that. Or this can be van der Waals or etc. So you resolve multiple particle contacts. You can take different models to model these contacts. Like the spring dashpot friction slider model, which actually was first proposed by Kundal and Strack, and Tsuji introduced that in the particle technology community. So, and we have a soft sphere collision, means you resolve in some way the deformation. So this is just summarized here. Lagrangian particle tracking with discrete particle method. Of course, you can also calculate here all real particles if you want. You have a standard Lagrangian particle tracking, or you can use the particle concept, and we have used the collision model. The collision does not appear in the equation of motion. The collision between the particles is separate model. You have to choose. Collision means binary collision, and the particles velocity changes, of course, due to the collision. So you track the particle. I put this beta inside the equation, which is the swarm corrected drag coefficient. And to account for there is no collision force, some people introduce here a collision force, which is of course not correct. You solve for the linear motion of the particle, rotational motion, and once a collision occurs, therefore you have time step limitation, you can only resolve binary collision. You calculate the impulse equation and solve for the new velocity of the considered particles. And DEM is this soft sphere particle collision, or discrete element method, has the big advantage that you can calculate these contact dominated systems. Packed beds, fluidized beds very easily. The Lagrangian or the discrete particle method has some problems at higher concentrations. Maybe you can, we have applied it already to volume fractions of 10 to 20%, but then the coupling becomes more sophisticated. So in this case, you resolve multiple particle contacts, of course considering the finite size of the particles. You track the particle motion by considering all fluid dynamic forces, external forces, and of course the contact forces. And again, here is the beta, this swarm drag correlation often used. For example, when epsilon approaches with larger than 0.8, then and u, and if it's smaller, you use the ergon correlation. And for each contact, you can use, for example, this spring dashboard slider, friction slider model. But there are also other models to describe the contact between the particles. If you go to hard-sphere collisions, you need basically two constants. The normal restitution ratio, but not constant. Parameters, these are not constant. The normal restitution ratio and the friction curve. And here you need some more information to describe the contact forces, like Young's module. This is the JKR model is used to describe the contact between. Okay, so this really you should distinguish discrete particle method with hard sphere collision, discrete element method with soft sphere. You can use the discrete element method also in a more dilute regime, but it's more expensive, of course. I think Behrend is doing that. I wouldn't do that. A hard sphere model is simpler, and you need less parameters to be. But in a dense situation, of course, the DM is very good approach. So collision modeling. It's basically the impact point of the interaction. Approach each other collide to find first the moment, when they collide, how they collide, then you can take the rebound. So there are these three approaches. This is the deterministic, fully deterministic approach to detect the collision. So you track two particles. This can be also partial. And you have to find the crossing of the trajectories, and you have to find the collision. Numerically, very heavy. So you have n times n minus 1 over 2 checks of neighboring particle arrangements. You can define some collision spheres to reduce this number. Mean free path and look for all particles only in this collision sphere. Then you have this deterministic stochastic stochastic model. This is the Guericke model. Basically, you track a parcel, and simultaneously you know the location of the parcel, and then you check whether there is a collision probability. You take collision frequency times delta t, whether there is a possibility of colliding in any of these particles. One control volume only, normally. Again, then this method is grid dependent. So suppose this particle is at the edge, then you should search more in this sphere regime rather than in the control volume. So there are approaches to account for. So, and the last one is our collision model we are using. It's fully stochastic. We don't need to know anything about the other particles. We can also do this sequential tracking of the particles. We just need to know cell-based information on the size distribution of the particles, on the size-velocity correlation of the particle. I will show you. So when we track this particle, we randomly generate a collision partner out of this cell based on these properties. Then we calculate the collision probability. If a collision takes place, we collide and rebound. Fictitious particle is not of interest, but we have to be careful when you have coalescence or breakup. Then, of course, you have to fulfill the mass balance. If the fictitious particle is added to the real particle, you have to change something. This I mentioned. So it's fully stochastic. You don't need to know anything about neighboring particles. You just need to know the properties in this control line, like this velocity. Very efficiently, very efficient, and also easy to parallelize because you are completely independent. You don't need to know about the particles in the other process. So what's the idea of this stochastic interparticle collision model? So we have a particle which is stretched through the flow field, and in each time step we create a fictitious collision partner, as I said, out of the cell properties. So we have the concentration of cell here with a certain size distribution of the particle. And first of all, you have this cumulative distribution. For example, you do a random process to select a certain size of this particle, this fictitious particle. Then you stored already the correlation between particle mean velocities, or mean components, of course, with the particle size, and also the fluctuating velocity. The assumption behind that model we used so far is that this velocity is represented by a normal distribution, which could be not always the case. Sometimes you also have a log normal distribution, but this is disregarded at the moment. But you could do it. So, and then later on you create the collision probability and check whether you have it. It's a bit cumbersome numerically, at least Oscar Scott extended completely open form to do this kind of averaging of the properties of Lagrangian particles, but it's very efficient. So now, again, back to turbulence. So we don't know the real velocity of the fictitious particle. We have to calculate it. We grab a value from the size velocity correlation, but is that true? You have to introduce also a correlation, because in reality, let's say two particles which are colliding are moving in the same eddy. So they have some correlated velocity. They are very inertial, they don't care. No correlated velocity. So we have to introduce this correlation in modifying the fictitious particle velocity. So the fluctuating particle velocity of the fictitious particle via a correlation function is created, it's only the fluctuating component, is created through this correlation function, which is a kind of Stokes number. So that means if the small Stokes number, the correlation function of 1, the fluctuating velocity of the fictitious particle is almost identical to the real one. If you have very inertial particles, the random part here, with a standard deviation of the velocity fluctuation, which is 1. Okay? And this correlation function was initially evaluated by doing Lagrangian point particle simulation and comparing it with LES of Simonet and Toulouse, and we got this let's see, this blue dashed line. Recently, Darboline has done some more simulations, more than 10 years ago, evaluated the particle pair distribution function and proposed this correlation. So then, having that, you have now the fictitious particle velocity, the real particle velocity, and their sizes, and then you can calculate the probability, and then you decide whether a collision takes place or not through a random number. When this random number becomes smaller than the collision probability, a collision happens. Okay, all the collision process is then done in a coordinate where one particle is fixed. Talk about agglomerates. Normally, the agglomerate is fixed, so you transform all the velocities, linear and angular velocities, and do the collision process. If we do so, we can easily generate the impact point. That's what we need. So we have this collision cylinder and the transformation is that the relative velocity vector is aligned with the axis of the collision cylinder. Okay, so the collision point can be only on the front hemisphere of the second particle. This is again done by a random process, and then you have a collision location and you do solve the impulse equation for an oblique collision of the particles. Okay, this is 100% impact efficient. Now, your question is probably, what is impact efficient? So, suppose you have a spray. You have droplets of 100 micron and droplets of 10 micron. If the 10 microns were no 100 micron grab small particles because there's a huge relative velocity and the number concentration of small particles or droplets is much higher. But the small particle can move with a relative flow around the collector. So it will not have a collision. So we have to define this impact efficiency. Luckily, my colleague from Karlsruhe many years ago has evaluated this impact efficiency for a spray scrubber, where droplets capture solid particles. And this problem is also present in three-phase flow, where you want to capture solid particles in the liquid with a bubble. Strong effect of impact efficiency. Basically, this means that only from a certain circular area the particles will hit the collector. The particles beyond this YC are moving around the collector. There will be no collision. So the collision rate is drastically reduced. And Tuch and Löffler provided, this is the definition, the diameter of this sphere here, circle is YC, and this is the diameter of the collector, and this squared, because you compare areas, is the impact efficiency. 10%, 20%, depending on the particle size. So the curves for this impact probability or efficiency has been provided for a range of Reynolds numbers, collector Reynolds numbers. And you see here a small collector Reynolds number, large collector Reynolds number. There is a difference. For large collector Reynolds numbers, you have a higher impact efficiency than for small ones, because then inertia effect is more important. And this is only valid for inertial effects. Diffusion effects are not valid. Okay, so then you have a collision only if your sample lateral displacement of the particle and A is smaller than YC. So that's the collision. Okay. Then you solve the equations, the impulse equations for translational velocity, for gravitational velocity. You have some boundary conditions, which is the Coulomb's law of friction, and the restitution ratio, which is the loss in the normal component, and these are plugged into the equation, and you have a solution for two possibilities: the sliding collision and rolling or non-sliding collision. And with that, you get the new velocity of your real particle. The fictitious particle is not anymore. Drop it and retransform all the velocities from this collision-based coordinates forward frame and continue calculation. This is, of course, done for every parcel in your domain or particle in your domain and for every time step. But nevertheless, it's much more efficient than any deterministic collision. Okay, just to illustrate the effect, I like this work we did that many years ago with simulated. It's again hit homogeneous isotropic turbulence box, but in this case we induce the particle motion under gravity, so it's 50g, no, not 50g, it's 5g, so 5 times the gravitational constant here, and these particles are sedimenting under the action of gravity in a homogeneous isotropic turbulence. Here are the parameters of turbulent structure, the length scales, the Kolmogorov scales, and yeah, to get collisions, you need 2 kinds of particles. Or to get more collisions, we introduce 2 kinds of particles. The particles are very large in this case, but the density is very low. So you have you have both particles are 650 microns. Particle A is only 170 grams per cubic centimeter, 117 kilograms per cubic meter, and particle B is 235. Due to the different weight, they have a different sedimentation velocity. Then we have a fixed volume fraction of A particles, and we vary the volume fraction of B particles. This is the result here. Picture on the left-hand side shows the mean velocity. LES are the closed symbols, LES from Simone, and the open symbols are our model calculations. And you see here, first alpha A is 1.3, 10 to the minus 2, so it's somewhere here, alpha A, and then we vary alpha B in this way. You see terminal velocity of fraction B is here, 3 meters per second. Terminal velocity of fraction A is 1.9 meters per second. So there is a large drift velocity to induce the collision. So what happens now? Why is this particle B slower than the terminal velocity? This particle B collides very frequently with particle A. So it's hindered in seconds by collision. But then when you increase volume fraction B now, you see that both velocities tend to approach the B velocity because particle number density of particles B are increasing. You have more frequent collisions. So these particles B drive now the A particles. Before they are hindered, so particle B is hindered in settling by A particles, and now B particles drive the A particles. We also looked at this is the comparison, which is not too bad. Also on the not turbulent kinetic energy of the particles, but fluctuating kinetic energy of the particles. Particles have no turbulence. This is again green is A and blue is B. You see some increase of the fluctuating velocity because of more collisions, but also the difference between LES and point particle simulations is slightly increasing, but the trends are okay. So we basically were satisfied. All these collisions were done with restitution ratio 1 and 0 friction. So now going to the collision frequencies, actually you can define 4 collision frequencies. Frequency AA, frequency BB, frequency AB, frequency BA. A and B and BA should be identical. So you see here, first of all, the triangles, which is the frequency between A and B. The symbols are, the red symbols are LES, so agreement is quite good. And the blue one is our point particle simulation. And of course, FAB grows as the volume fraction of A particles is increasing on number 10. Then you have also a slight increase of AA, so the collision frequency between A particles, mainly due to the increase of fluctuating velocity. So this is a nice test case, and I think demonstrates the effect of interparticle collision. So it's not too dense, so the volume fraction is here 1%, roughly, and the maximum 1, 2, 3, 4%. So, particle clustering in turbulence with interparticle collision. We know the physicists like that. Clustering of particles in homogeneous isotope turbulence. And maybe I start with a picture. That's going to happen. So you generate a box with homogeneous isotropic turbulence in your computer, and this is again done by point particle Boltzmann method. And you track particles of different size, respectively different densities in this case. You have low Stokes number particles, volume fraction is 10 to the minus 3 in our cases. Oh, nice, you have a nice structure. It's just a sheet through the box, of course. And you have a nice distribution of the particles, almost homogeneous. Okay, now you increase the Stokes number, you arrive at about 1. Oh, strong clustering. Clustering occurs mainly in regions of high strain rate and low vorticity. So thinking, clustering might induce interparticle collision. That was our idea. None of the physicists looked at interparticle collision at that time. And now you go further. You increase the Stokes number 10, and again you get a homogeneous distribution. So that is no low Stokes number, no clustering, intermediate Stokes number clustering, high Stokes number, no clustering. So let's go back. These are basically the conditions. It's a 1 to 8 cubed box. We have here the viscosity, the fluctuating velocity, dissipation rate, the integral length scale over the box size, 11%. The integral length scale over the Kolmogorov time scale is 5. This is the Kolmogorov length time scale. Right? This is the length scale over the grid size is about 1. Of course, what is DNS? DNS means you have to resolve all the scales. Normally, it means that your grid should be smaller than Kolmogorov length scale. But in many cases, the people take a value around 1. So Taylor-Reynolds. And here are the particles, Lagrange tracking of point particles, only drag, no gravity. Then constant particle diameter, 0.2 k. So the particle is also smaller than the grid size, of course, and we vary the density of the particle. We have imposed here or used a deterministic interparticle collision model. These are the different definitions of the length scale and scale of Kolmogorov. Here are the references if you want to have a detailed look. So what happens now is you need to quantify the degree of accumulation, and that's done here. There are very different methods, Born-Noy function and others, but we just use here the particle segregation parameter, where you compare the spatial distribution or the RMS value of the spatial particle distribution with the Poisson distribution. The Poisson distribution is shown here. Now, if you have this regular arrangement, of course in 3D, therefore the number is 8, you have a delta function in this case. Now you have here more or less random uncorrelated distribution of the particles, so you get a very small difference in these two values. So Poisson distribution is almost identical to the value. And now you have this clustering. You see here, this is the distribution for particle number in the box, and this is for Poisson distribution, and you see this difference is good. So what we expect is this value for small Stokes number is small, increases, and you can also use this. Let me see. Of course, you can also apply this fractal dimension to get information of the particle distribution. This is normally done only to characterize agglomerate. So where you calculate basically the number of particles over radial position, like here, the control volume, and then you draw a line through these points, which you measure. Hopefully, they are along a line, and then you get a kind of fractal dimension, which I will not use here. So that's the result. Particle dispersion in frozen heat. Nevertheless, we have one powerful computer with many particles. It takes some time to do this simulations. Transient, fully transient. So you calculate flow field, particle breaking, all sequentially. So in some cases, to do the analysis, we just take a frozen flow field, a certain flow field at a certain time to track the particle. And this is illustrated here. This is, and also then you have a better comparison, because then the particles behave in the same way. And now we switch off and on interparticle collisions and can see what happens. And that's done here. If you look at this cluster, they are more concentrated, of course, if you have no interparticle collisions. And if you have interparticle collisions, they are more dispersed. So interparticle collisions tend to disperse such a cluster. It's not always a dispersion effect, as I showed in this pneumatic conveying. You have also a capturing effect. So this should be a nice video. So left is no collision, although you will not see a big difference. Come on, no. Yeah. Okay, it might be a bit hard. And the coloring indicates the framework. Oh, you see, just for fun. Okay, to quantify this effect, this is illustrated here. We have the segregation parameter plotted versus the Stokes number. Low Stokes number, we are here. Then it increases, as I said before, it decreases again. And there are three volume fractions considered. I have to look now. Yeah, this is fully turbulent, not frozen. So you see here the low volume fraction, there's hardly any difference. Collisions are not important. Then the blue, also not very much. But here you see that the red symbol or the closed symbols are with interparticle collision. That interparticle collision tend to reduce the segregation parameter, which means it's a dispersive effect. Unfortunately, we would have liked to go to higher volume fractions, but then the computation at that time, simulation, at that time it was still too expensive, although we used it for point particles. Okay, now the interesting part, importance of modeling of agglomeration. So agglomeration is very often used on purpose to build bigger particles. Sometimes not. If you do a measurement, for example, of the particle size, agglomeration is disturbed. You want to know the primary particle size, not the agglomeration. But here, for example, when it is a spray dryer agglomeration is of favor. You want to produce from a suspension solid particles at the end. Therefore, you spray liquid or suspension, you dry it, and at the end you have solid particles. mostly you have agglomeration forming these kind of particles. We clearly can identify the primary particles, and there is some merging of these particles. Then another example is this flame synthesis, which we use to produce nanoparticles, and also they are clustering and agglomerating, and you have very fluffy agglomeration. Here is more compact, here is more fluffy, and you use the fractal dimension to distinguish. Yeah, here in the spray dryer, it's also a special case when you inject the spray and additionally define product coming out of the process. You inject it back and particles agglomerate. And fluidized bed granulation, same, you like the particles sticking together, other particles. And a very nice phenomenon we observe cyclic separators. When you agglomerate the fine particles, they are, of course, easier separated. So this is the way we can characterize. Oh, this cannot be good. Okay. To characterize agglomerate properties, there are different ways. Of course, we know the volume, surface area, specific surface area. Interesting. We have very often used the convex hull, which is illustrated here. So if you have an agglomerate, you wrap a hull, convex hull around this agglomerate, and you get a certain porosity of the agglomerate. You also can, with the convex hull, calculate a proper equivalent diameter. This is a compact aggregate with 30 primary particles. Then aggregate density is a result. What you take away the aggregate easily, but what is the volume? You take the volume of the primary particle. So you take, for example, the volume of this convex hull to get the porosity or the density of this porous aggregate. Volume equivalent diameter doesn't tell you very much. See, that means all the primary particles are compacted to a single sphere. Outer radius is more interesting. I illustrate that here. This is the red radius, which is hard to get numerically and also hard to measure. So volume equivalent is more easy. You just measure the volume of all the particles involved, and then you have a volume equivalent size. What's very often used is the gyration radius. That's the difference. You choose a reference point, and you measure the distance to all primary particles involved in this aggregate, and you build an average value, which somehow characterizes the distribution of these primary particles inside the aggregate. You have a very fluffy aggregate, fractal aggregate with dendrites, then you have a large value. If you have a more compact aggregate with the same volume, you have a smaller average value. Porosity is, of course, interesting, but only in connection with the convex hull, for example. Sphericity is less meaningful here because you have a huge surface area. Volume equivalent here is clear, but the aggregate surface is very huge, depending on the number of primary particles involved, so it's less meaningful. And the fractal dimension, as I mentioned before, describes you how the mass is distributed over the radius. Maybe you know, fractal dimension 1 is a line of particles. Fractal dimension 3 is a compact sphere. So these are the means to characterize aggregate. But now the question is how to deal with an aggregate in a numerical computation. First of all, aggregate motion, because the aggregate is not a volume or it's not a sphere. If you switch on a commercial code and start, then it says your particle is a sphere. and the point mass. It's not a sphere. So first of all, you need to know some kind of equivalent diameter to get proper values for weight, width, and so on. Okay, which is the proper value? The compact sphere, so this is the blue circle, is of course not correct. Right? The resistance of the aggregate is probably much higher. So what we mostly did is taking the gyration diameter, because this can be evaluated during the calculation. The enwrapping sphere is hard to get. Right? You have to post-process somehow aggregate data of 10. Then if you have now this, let's say, this gyration diameter and the gyration sphere, do you need to account for porosity in your drag coefficient? Of course, there is some effect, some slight reduction of the drag. Are there correlations available? No, nothing. So mostly so far, the agglomerate volume is 0 curve. Then the other effect is on collision. Now I have a volume, I treat my aggregate as a volume equivalent sphere, then the collision rate with other primal particles is much lower. Only if I account for, let's say, this enwrapping sphere diameter, your collision rate is much higher than with this spherical particle. But there are also locations where this particle is not hitting, missing the aggregate. So then what's the correct cross section? Is there an impact efficiency? So if you see in this picture, yes, there is an impact. Influence of porosity. Okay, nice problems, which we have to tackle somehow to go to calculations of aggregations in a problem. So in principle, you have to do your collision model, and then you decide, do these two particles stick together or not? That's the first step you need to decide. There is a collision, but do they stick? Then you have to take some accretion. Like Van der Waals, electrostatic forces is already a big problem because you don't know how these particles are charged. So we just restrict ourselves to Van der Waals force. So on the left-hand side is rebound. Okay? But the criterion is yet missing. And it will be a critical velocity. So rebound can be easily calculated. I showed the equation before, and here just without rotation of the particles. Now, if, let's say, the particles collide with the velocity being under a critical velocity, they stick together, okay, and form an aggregate. Then what we do with the structure, what we do with the size of the aggregate. Before we go there, I just briefly showed this slide. There are many options to calculate the possibility of fusion. We just took this work of, it's also coming from Karlsruhe, where they look at particle separation on fiber media. And you compare the kinetic energy of the particles before they collide with the Van der Waals energy and dissipating energy. If this Van der Waals plus dissipated energy are larger than the kinetic energy, you are sticking. And if you do all the mathematics, you have to do the integration, involves a Harmacher constant. This is A is the deformation area, it's here, and the minimum contact. And this is the definition of the restitution ratio. Doing that, you end up with the critical velocity. Adding additional parameters, as I said, additional parameters makes a calibration, or when you have additional parameters, you need a calibration of the model. So here you have this minimum contact distance, which was taken to be 4 angstrom. Then you have also this yield pressure, T3. So these are the two main constants And of course, you have 3 Amaker constant into restitution. So we have taken these values from the particular used them. So what happens now if the collision velocity normal to the other particle is smaller than the critical velocity? Yeah? You have larger velocity, they rebound. Okay? Now what you do with the size? We try to do that, or I try to summarize that. On the left-hand side is the straightforward model, no good model. So you assume after aggregation the particle volume equivalent sphere, you track the particle with the volume equivalent sphere, and you do the collision with the volume. It does not give you very many information on the aggregation property. It gives you a number of primary particles, maybe if you have penetration. So far, I will not show results on that. If you have a straight run, you have mushy particles. When they collide, they penetrate partially. So the penetration changes the porosity. So it's not the best model, but it's mostly done so far. So then we have this sequential model, which was actually more than 10 years developed by my group. We will show more, which sequential, why we have only, or we are only considering the collision of 2 particles. And then with the void between these two, we put a convex hull around it, and with the void we form a new volume equivalent sphere with porosity. Okay? So it's very effective. You get the number of primary particles, you get the hull volume diameter with porosity, you get this porosity, and we also store contact forces to look at the possible breakup. This on the right-hand side, okay, it was a nice study, but it's a very complex model, very computationally demanding. We have not yet done many large-scale systems, but the idea is to store all locations of the primary particle. So we get aggregate structure, fractal dimension, effective surface area, volume of the convex hull, porosity. So this is the approach done for the volume equivalent sphere in the parcel concept and the fictitious interparticle collision model. So when you have agglomeration, you form a new volume equivalent sphere, so your diameter increases. So you add a fictitious particle to your real particle. So the mass would be increasing, but this should be avoided for mass balance. Therefore, you reduce the number of primary particles in the aggregate. Okay? That's very important. Mass balance going on. And so we track particle, but we have also a certain number of real particles. This is only a number. It can be 1 million, 1,000, or 1.01. That's to capture the mass balance correctly. So you are doing that, you increase the size, but you decrease the number of primary particles in the aggregate. So this is the sequential model, which also was used by Oscar. So the aggregate volume is particle 1 plus particle 2 plus the void volume, which is the green area. This is the second sphere attaching to that. You only have pairwise addition. And pairwise means you have 2 volumes of the particles and you have 1 void volume. And it's added to form a new volume equivalent sphere. No, a new sphere with porosity and all the volume of the particles included. So it's a porous sphere which gives you the correct density. And this is done, you can collect hundreds of primary particles. Problem, but they are porous. You can store these contact points. pulse force, for example, in order to model also a breaker. Numerically quite efficient, and we did pipeline simulations with that. So now the very complex one. This is the structure model done by Mr. Stübing. So basically, you store these particle locations in a linked list. The idea, you have a starting particle, and you store reference vectors to all the primary particles involved in this aggregate. Okay, this is not a problem to do that computationally, but you need to know now how to deal with this cluster of primary particles, how to do a collision. So, and this is illustrated here. First of all, the assumption, agglomerate can only collide with primary particles. My fictitious particle cannot be an aggregate. That simplifies the thing. Assuming that number concentration of aggregate is lower number concentration. So, first you calculate this fictitious particle, and this fictitious particle collides with this aggregate structure, and you have to assume a certain diameter here. As I said, mostly we have taken the vibration diameter, because this is easily accessible in the calculation. The Redmond sphere diameter is more difficult. You have to analyze the aggregate. How is the structure? So we account for this impact efficiency and distribution, and we select the point of impact randomly. Having this point of impact, we have this lateral displacement and yc. We can account for this impact efficiency. This point is now moving there. As we do not track the rotation of the aggregate, possible, but makes it more complex. Before we attach the new particles to the aggregate, we do a random rotation. So this is done, and now we find particle number 2. So this new particle collides exactly with particle number 2, and now we just have to prove or check whether it's sticking or not. Okay? Understood? First of all, we create a fictitious primary particle colliding with our aggregate, which is being tracked. Then we calculate the collision probability and decide if collision takes place. If so, we have to account for the impact efficiency. Then we do this random rotation and find the nearest neighbor inside the aggregate and collide the primary particle with this nearest neighbor. So that's added to the system, and then we can either have a rebound. This particle can be also rebounding depending on the critical velocity, or you have a sticking here, and another option would be this penetration. So then, let's say we have a new aggregate and we change the properties, or we update the properties of the aggregate. So we did some calculations. Jonathan, what I should stop at what time? Yeah, but the restaurant is. Yeah, okay. 2 hours are actually more than 30 minutes. Okay. So here are the parameters we use. We consider, again, we take a hit homogeneous isotropic turbulence, but this is very simple since we do not simulate the turbulence. We just mimic the turbulence. When the particle moves through the turbulence, we just create a fluctuating velocity from the flow to calculate the instantaneous field velocity. Mean velocity 0, we just randomize the fluctuating velocity. So then we know the relative velocity between particles. 5 micron particles, 12 micron, and the size distribution 2 to 20. Volume fraction is 1 times 10 to the minus. Our Stokes numbers are here. 0.08, 0.45, and of course here we have a spectrum. And I said we need these parameters. For angstrom was the distance, 14 nanometers. Then this is the limiting pressure, friction coefficient, restitution ratio, and how much of it. Of course, these parameters are material dependent. Also, you can use you could also use the JDR, more advanced JDR model, which includes Poisson ratio and other parameters. We track 10,000 computational particles through this box. So first of all calculations I'm showing here are done with a gyration diameter with some parameters. So not the rapid time. Now we have done two calculations. Here this shows the number of aggregates in the flow. Here you show, see what the difference here, the number of particles included in each aggregate, and here is the gyration line. Without impact efficiency gives you blue line. So a very wide distribution of cycles, ranging from 0 or 2 primary particles until 160. So what happens with impact efficiency? Of course, particles might go around the aggregate and not collide. Then we have this distribution. So a huge difference. So impact efficiency in this respect is important. Yes, you should know that we have a porous structure. So particles might also go through the aggregate, which is not accounted, it's accounted for, but not in the impact efficiency. On the right-hand side, we have the gyration diameter. So without impact efficiency, 20 micron particles, and with impact efficiency, with 60. So the particles are looking like this, close to reality, although never look really on the structure. Are they dendrite-like or compact? This is another issue which has to be evaluated. How can you influence this? Just the outcome of our random process. There should be, of course, a physical phenomenon determining whether it's compact or dendrite structure. So here we have again number of collisions versus type of particle we consider. So here, VES, the aggregate is a volume equivalent sphere. Gyration, the aggregate is followed by the aggregate gyration diameter. Okay, it's larger, and this is the bounding sphere. So of course, with the bounding sphere, you get most collisions. This is without the blue, without impact. But now with impact efficiency, they are almost identical. I forgot to search for the number, but it doesn't matter whether you take VES, gyration, or bounding sphere. But what can happen here? This is volume equivalent sphere, gyration, and bounding sphere. Let's start on the right-hand side, or let's stay to this. The red part is missed. That means the new particle does not find the nearest neighbor and goes through the aggregate structure. Okay? Then it's red. Blue is rebound, so the impact velocity is too high. Rebounds, no sticking, and only this portion is aggregation, which is slightly changing because structure becomes more porous when you take a bigger diameter, like the wrapping or bounding sphere diameter. You have more collisions missing the aggregate. So some results. These are again some aggregates. This is with size distribution and also this one. And to see the evolution, relative number of aggregates, number of primary particles in time. Of course, it's growing. Then you see the gyration diameter, it's also brown, and the PDF is somehow changing. The beginning is normal distributed, and at the end it's skewed to one side. Again, tracking with gyration diameter, collision detection with gyration diameter. This is the porosity of the hull, and the fractal dimension is reduced, of course, right? 3 is our sphere, 1 is our linear chain of particles, so the fractal dimension moves to around mean value 2. So I showed at the beginning a suit particle, fractal dimension somehow 1.8. Okay, we can also take mean values and we look at the difference between mono-sized particles and fully sized particles with the same mean size. So the mean size here is also 12. And you see mono-sized, and this is time again average particle number in the aggregate. It's slightly growing, but if you have a poly-sized size distribution, it's growing faster because you have more fine particles. Finer particles have stronger adhesion forces and easier stick to the aggregate. So there's pretty much of physics included in this model. And here is the relative size, diameter over mean diameter for taking just a volume equivalent sphere. That's the open symbol. It's here, and the right one is here. So you under-predict, of course, remarkably the diameter of the produced aggregate. Only if you take the gyration diameter, you get a proper increase in time growing aggregate. Yeah, this is the last slide for this part, showing again the development of fractal dimension and porosity. I have to think porosity are the open symbols. So it's here. So the porosity grows from 40% somehow for a two-particle or small number of primary particles towards about more than 60%. And here you see the decrease of the fractal dimension. And again, the behavior of mono-sized and poly-sized particles is different. Okay, so if you allow, I take 10 minutes for the cycling of Oskar Sprott. He actually did all the work implementing stochastic. So in this case, we use LES, not any simulation. Those are strongly anisotropic with respect to turbulence. So if you use any runs model, it doesn't work at all. So we took LES. In this case, we use dynamics Magdeburg model. We use two-way coupling, momentum coupling. There is no effect of the particles yet on the turbulence. We are working on that because Magdeburg is an eddy viscosity model. So it's difficult to modify the eddy viscosity properly due to coupling. Not straightforward. We can easily do it for bubble-induced turbulence. Many people do that, but not for the dissipation. Then we, however, consider this SGS turbulence in particle tracking. If there is some time after lunch, I could show a few slides on this. Particle tracking is done with drag, gravity, buoyancy, shear lift, and rotation. Although the particles are less than 20 microns, we consider rotation. Normally, the viscous damping is very strong. So, this is the agglomeration model. You see that we compared simple simulation of 15 primary particles. So, this is the sequential model. Here, This sphere model, of course, the diameter growth is completely different because the sequential model accounts for porosity. This is aggregate porosity, approaching here 60% roughly. And this, of course, as we have porosity, we have a reduced density of the particle. So this is the sphere size, 30 micron roughly, and here with the sequential model corresponding, you get 60 micron. And then he demonstrated that video. So you see, this was monocyte. No porosity. Then sequential model that has the box particles. You see how tight distribution. This is the interesting result. Okay. The way the results are obtained with the structure model showed before. And the lines are obtained with the sequential model and with the sphere model. You see here the agglomerate size with the number of primary particles. Here you see the porosity with the number of primary particles. This line is the so, agreement is almost perfect. I think you can live easily with the history model to really properly the agglomeration of particles, properly calculate separation. I will not talk about it. So, this is the German cycling we looked at with tangential injection, burning flow goes down, this is your collection bin, and this is the exercise water binder, and you get, of course, typical tangential velocity profile, free profile underneath the exercise, and here is the mean tangential velocity, the rating velocity. The dots are experiments from extract, and the lines are simulations with different grid size for 1 million. And of course, the tangential velocity, yes, everybody here knows how a cycle works. Due to centrifuging, particles go to the wall. And this is the structure of the particle concentration. You know, these kind of ropes develop down. The nerves perfectly capture the street line of the center of the rope, as in the experiment. Here are some dimensions. It's 300 millimeters per second. And you see and then the output. See, this is two-way coupling. And this is four-way coupling. You see, I showed you the convey that inter-particle collisions can capture particles. So particles are moving towards the wall, and those particles who want to escape from the wall are hit by these particles, pushed back to the wall. So therefore your concentration increases. Then you have here four-way coupling with agglomeration. This is particle concentration meter. So in this case, somehow the work structure can be recovered. There is no big difference between these. So here are interparticle collision rates. Four-way coupling, we have 99 10 to the 6th power collisions per second. If you, of course, have an agglomeration model, here these are the interparticle collisions in 1 second. We have a lot here, less here. You see that the collision rate is first of all reduced, but the aggregates are more formed in the upper part. Then the collision rate is reduced because many small particles are already captured, so that the collision rate goes down to 50 or 53 10 to the 6. So then here you see the agglomeration rate. Oh, sorry. There are more down here. Agglomeration rate is slightly higher in the sequential model because the size of the aggregate is large. So that's the most exciting, but it's not so easy to get change in to characterize excitement. We plot basically the net of the number of particles separated in the field over the injected number of particles. But here we did it a little bit different to show this. So the efficiency is 1 minus escape particles over injected particles. Escape means those particles going out of the exit. So this gives a better picture. So first of all, one-way coupling. I cannot show this. Separation efficiency too high. It's the black bar. Excellent. Right. Two-way coupling, of course, modifies the tangential velocity. Two-way coupling reduces tangential velocity, therefore the separation efficiency goes down. So we have two-way coupling here. Blue is four-way coupling. This is the battery type. Very fine. Up to 10 minus. So 55, 0, 20. So now we switch on aggregation. Green one is clear model. It's nice. Switch on now aggregation, separation is improved. But only if you can do the calculation first. You take, of course, the connected number of particles to bigger. I take count all the primary particles. So you have a drastic increase, I would say, of the separation efficiency and you improve the fine particle separation considerably. Now, if you take the sequential model, it's slightly reduced. Yeah, why? Let me continue. What do you do in a cycle? Take the center, place your particle there, and compare centrifugal force with strain. The next of an aggregate is the same as the volume. The size now is size. The poorest aggregate with bigger sizes, so the gradient is becoming fast. So it's not simple. So this model is slightly worse. Okay. I think it's not really. So the last picture. Left is a simulation with penetration. But primary particles, like in spray area, are now to penetrate. So look on the left, simulating aggregate, semantic aggregate. They are very, very good. I think with this aggregation model, you can learn a lot. And for doing really industrial simulation, very good. We have done extension for breakup, which of course excited the first visual interparticle solution. Shear rate is less important, but also worth it. So this Oscar has also done. So I hope you enjoyed it. If you have questions, ask me. anytime. Thank you very much.
Okay, thank you, Professor. I'm sorry? Less than hours, okay. Any questions for Professor Sommerfeld? I was wondering if there is a model to destruction of the agglomerates. Yeah.
Breakup mainly occurs between work conditions, also collisions between primary markets and aggregate. There is some breakup, but I don't so at least the first step is done.
Yeah, but it changes a lot or not?
Not so.
Yeah. Because I'm thinking in a CFB, you know, like a fluidized bed or circulating fluidized bed where we don't have too much wall collision. For sure we have, but not as in a cyclone flow. Yeah.
Each year.
Yeah. Okay. Thank you again, Professor. I would like to offer you a gift of this coal here. This one. Thank you for your visit again. Yeah. It's a brick. It's a brick.
From the mountain area, yes.
Ok.
Okay.
Então, pessoal, teremos um tempo para o almoço agora. A gente retorna à tarde com a nossa programação. E à tarde a gente vai dar avisos sobre o restante da programação, especialmente sobre hoje à noite. Ok? Obrigado. Até lá.